Hello, in this video we are continuing our discussion of section 6.2 with trigonometric substitutions. Specifically, we're going to be working through example 1, which has asked us to evaluate the integral from 0 to 1 of x squared over the square root of 4 minus x squared dx. So the first thing that we need to notice here is that this has the same form as our intro, which is a squared minus x squared, with specifically a equaling 2 because of the fact that 4 minus x squared is equal to 2 squared minus x squared. So this means that we are going to use the same substitution. X equals a sine theta, which in this case is going to be 2 sine theta. That gives us then that dx is going to be 2 cosine theta d theta. And now we can rewrite our integral. So the integral from 0 to 1 of x squared over the square root of 4 minus x squared dx is equal to the integral. I'm going to come back to the bounds in a second. X is equal to 2 sine theta. So that all gets squared, and then we have over the square root of 4 minus x, which is 2 sine theta, squared dx is 2 cosine theta d theta. Now coming back to the bounds of integration, just like with a u substitution, we need new bounds. And we are going to use the substitution to find those new bounds. So we have x is equal to 2 sine of theta. First off, when x is equal to 0, this means that 0 is equal to 2 times the sine of theta. So the sine of theta, if we divide both sides by 2, is going to be 0. So then we are looking for a theta value that gives us an angle that gives us a sine value of 0. So this means that theta is going to be 0. In other words, this is the angle that gives a sine value of 0. Now, when x equals 1, we have 1 is equal to 2 sine theta. Dividing both sides by 2, we get 1/2 is equal to the sine of theta. So now we need the angle that gives a sine value of 1/2. So sine is equal to 1/2. Oops. That got messed up for some reason. Sine value of, this should be 1/2. There we go. What was I saying? Let me see. Sine has a value of 1/2 at pi over 6. So that is what theta is equal to. So this pi over 6 is our new upper bound, because x equals 1 was our old upper bound. And theta equals 0 is our new lower bound, because of the fact that x equals 0 was our old lower bound. Oops, bound. Let me try that again. There we go. So what we have then, if we write in our bounds of integration, we have 0 and pi over 6. Okay, so let me rewrite it here. So in other words, to make it a little bit easier to understand, we have the integral from 0 to 1 of x squared dx over the square root of 4 minus x squared is equal to the integral from 0 to pi over 6. of, let's see, 2 sine theta all squared over the square root of 4 minus 2 sine theta all squared, and then we'll have a 2 cosine theta d theta. Now, like what we did with the introductory example, let's simplify. So in the numerator, we're going to have 4 sine squared theta times 2 cosine theta. We'll have a d theta, of course, and we've got the square root of 4 minus 4 sine squared theta. And let's just do a quick side note. This is equal to 4 times 1 minus sine squared theta. So that's equal to 4 times cosine squared of theta. And if we have all of that under square root, we're going to end up with 2 cosine theta. So let's rewrite all the rest of our pieces. We have the integral from 0 to pi over 6. We're going to end up with the integral from 0 to pi over 6 of, let's see, 8 sine squared theta times cosine of theta all over 2 cosine of theta d theta. Now our cosines will cancel. Some of the constants will cancel, and I will pull the rest of that out of the integrand so that we have 4 times the integral from 0 to pi over 6 of sine squared theta d theta. This is an even power of sine, which was one of our exceptions. This means that we need to use the half angle identity. Which is, sine squared theta is equal to 1 minus, let me squeeze this in, cosine of 2 theta, over 2. So we get 4 times the integral from 0 to pi over 6 of 1 minus cosine of 2 theta all over 2 with a d theta. The 2 in the denominator I'm going to pull out and combine it with the 4 there to end up having just a 2 outside of the integral. And then we have the integral from 0 to pi over 6 of 1 minus the cosine of 2 theta d theta. Now, if we integrate our each one of our pieces, a big thing to notice is that we are integrating with respect to theta. With respect to theta, which means that when we integrate 1 with respect to theta, it's going to become theta, not x, not t, but theta. Okay. Then we also have minus cosine will integrate to a sine of 2 theta, a small substitution if you want to do it there. Will give you a 1/2 in front, and this all is integrated from 0 to pi over 6. So now we just need to plug in our bounds. We're going to have 2 times plugging in pi over 6 for theta, then we have minus 1/2 sine of 2 times pi over 6, which is going to be pi over 3, then minus 0 minus 1/2 times the sine of 0. Nicely enough, that should be a 0. Nicely enough, all of those terms end up going to 0, so all you really have to do is evaluate the first part. The sine of pi over 3 is equal to the square root of 3 over 2. So we get this is equal to, I'm going to distribute my 2 in the next step. Distribute 2 so that we get pi over 3 minus 2 times 1/2 will cancel out, and we've got a root 3 over 2. So in summary, the integral from 0 to 1 of x squared dx over the square root of 4 minus x squared is equal to pi over 3 minus the square root of 3 over 2. So this example shows you all of the details of using a trig substitution with a definite integral. It's very similar to a u substitution in that you have to find new bounds of integration. We still haven't dealt with trig substitution with indefinite integrals, but that requires a little bit more work because of the fact that we have to put our final answer back in terms of x or whatever our original variable is. So we will see that a little bit later in this lecture and then in some examples tomorrow.